Welcome back, everyone. Dr. Rhett Smith for ProtonGuru.com, going over lesson 6.12 today. In our last lesson, we talked about the reactivity of carboxylic acids and esters with oxygen-centered nucleophiles. And before that, we talked about some problems that we have if we try to use a carboxylic acid with a basic nucleophile like an amine. Now, if we don't have an acidic site here, we don't have the problem we talked about with carboxylic acids being deprotonated by amines. So esters can actually react directly with amines to make amides. And I want to show you how to make the amides here in this lesson. Of course, the first step for the ester is to do a nucleophilic addition of the amine to that species. And if we're going to use ammonia, we call this process aminolysis. That would be if both these R groups were hydrogens. But if we use a primary or secondary amine, this is called amidation. The product of nucleophilic addition would look like this species in box A. Now you may remember in the transesterification reaction we use an excess of the alcohol to react with the ester. So here we're going to use at least 2 equivalents of the amine to react with the ester. And the role of that second equivalent of the amine will be to help shuffle these protons around. And here I'm going to show it deprotonating that amine group there. And that gets us to the species we see in box B. Now you see we have a proton source and we have this negatively charged oxygen. Now you can draw a variety of different ways to shuffle this proton around, but the productive stage, you see these are all equilibrium processes, will be to push the electrons down this way. Now you're not going to make an alkoxide super basic anion when you've got a proton source right here. Instead you're going to protonate the alkoxide at the same time. That will lead to the production of an alcohol from this HOR prime group going together. You regenerated your amine and you've got your amide. Now notice that in order for this process to work, there is a step where you have to take an H away from the nitrogen. So you can't use N with 3 R groups. You can only use ammonia, which is NH3, or primary or secondary amine, so the nitrogen has 2 or 1 hydrogens respectively. You may also remember from our previous lesson, lesson 6.12, that esters can undergo acid-catalyzed hydrolysis or base-catalyzed hydrolysis to give you carboxylic acids. Well, amides are the least reactive of the carbonyl functional groups we talk about, but they can also undergo acid-catalyzed hydrolysis, just like the esters do. It usually just takes a little bit higher temperature to accomplish this. And of course, the acid catalyst has the role of first protonating the carbonyl carbon to activate that group to more quickly react with the nucleophile. In the case of a hydrolysis, of course your nucleophile is water. Now generically represented, some type of proton acceptor B could be another molecule of water, for example, usually used in excess. You'd be able to deprotonate that OH, leading to a species like this. Now these are all reversible steps, and you can put the proton back on here, but to go in the forward direction, you actually protonate that amine. And that's actually a little more favorable than going back to protonate the O, because nitrogen is not as electronegative as oxygen and can better handle or stabilize that positive charge. At that point, you can push the electrons down from the oxygen to make an O-C double bond and kick that leaving group amine off. Now you can take that amine that you just kicked off, or some that you have from another molecule, and deprotonate that O to give you the carboxylic acid and the ammonium salt. Again, each of these steps is reversible. So if we really want to do a productive reaction from an amide, like this one, to a carboxylic acid, like this one, we would need to use an excess of water. And of course, amides already being relatively unreactive benefit greatly from having this catalytic amount of acid present to help activate those carbonyls. Now we're going to use the fact that we can take amides and hydrolyze them to make carboxylic acids to show you an important synthetic route called the Gabriel synthesis. And like the development of any new synthetic strategy, you try to start with a problem that needs to be addressed. And one problem is that primary amines are pretty valuable compounds to make. And people could make them from ammonia and, say, alkyl bromides. Because the nitrogen has a lone pair, you can do a reasonably good SN2 type reaction like this. And in that way, you would make an ammonium salt. You can envision adjusting the pH to make this in the deprotonated primary amine form. but that amine still has a lone pair, so that amine can still attack the alkyl bromide, and you can actually get a second of these R groups attached to nitrogen. Adjust the pH so it's neutral. You can get a third attached, and these reactions are pretty easy to do. In fact, you can even take this guy attack again on the alkyl halide and make the ammonium salt. So if you try to do this and you heat it up to temperatures needed for the reaction, you actually get up to 4 R groups on the nitrogen, so you get a mixture of 4 products. Well, anytime you make a mixture of 4 products and you're actually trying to get, say, the primary amine that I mentioned was so valuable, you're wasting a lot of material. So that's not environmentally friendly, it's not economically friendly. This is not a good process for making primary amines. This leads to the Gabriel synthesis. And what we observe is that if you take this very, very particular, unique starting material called phthalimide, and you do these steps, react to sodium hydroxide, add a primary alkyl halide, add some acid, then add some base. At the end of this whole process, you will get this compound, and you will get your primary amine, which has whatever R group you had added in this primary alkyl halide step. So this is what we observe, but what's the mechanism of the Gabriel synthesis? How could we have possibly predicted this would happen, or how do we reason through how it could happen now that we know the products? Well, having just learned amide hydrolysis, there aren't any actual new reactions to learn, although it looks like a complicated process. If we add a base in the first step of the Gabriel synthesis, it's simply going to find the most acidic H on this molecule and take that away. Remembering that the most acidic hydrogen is the one that leaves behind the most stable conjugate base, it makes sense that we would take the proton from this nitrogen, because we have a resonance stabilized anion with a minus charge on nitrogen, like I show you in box A. Once we have that anion, if you look back at the steps, right, we've added the base already, so check. The next step is to add your primary alkyl halide. In this example, I just use R, but let's say it's a primary group like a methyl or something. All right, we're going to do an SN2 reaction using the nice nucleophile we just made, this anion, and that will get us the species we show in box B. So let's look back at our Gabriel synthesis steps. We've done the first 2 steps. Our next step is to add water and acid. Well, we just learned that if I add water and acid to an amide, I will get eventually to the carboxylic acid and the ammonium salt. Here, this phthalimide-derived species actually has 2 bonds from a nitrogen to a carbonyl, so it's kind of like a double amide. So we're going to hydrolyze both of those bonds, leading to a species like this, where we don't have the bond from the carbonyl carbon to the nitrogen anymore, and instead, just like the hydrolysis of a single amide, we have the carboxylic acid, so the OH wherever we had the bond from the carbonyl carbon to the nitrogen. It just happens to be twice in this case. And we have this piece that we've hydrolyzed off, right? We have the N, R, and we're in acidic conditions, so it's the ammonium, just like we had with the acid-catalyzed hydrolysis of amides. Now, I started off this whole discussion by saying we wanted to isolate these species, primary amines, not ammonium salts. So we have to add some base to adjust the pH so that we take a proton away from this ammonium. Now the pKa of ammonium salts is, let's say, about 9. It's going to vary wildly depending on what the substituents beside are, but let's say about 9. And let's say that the pK of this is maybe 5-ish, 4 to 5, let's say. Well, if we adjust the pH to be high enough to take the proton off of the ammonium, it's also going to take the protons off of the carboxylic acid units. So what we will get is the deprotonated version, the carboxylate, of this initially formed bis carboxylic acid. And then we finally have our neutralized primary amine, which was our target at the beginning. Now the fact that you have deprotonated this species on the left to make a carboxylate and have a neutral species here, the amine, means it becomes very easy to separate these. Ionic compounds tend to be soluble in water. So if I do an extraction, a liquid-liquid extraction, I would have the ability to solubilize this species in the water layer and this species in the organic layer. If you're taking an organic chemistry sequence with lab, you've certainly used liquid-liquid extraction processes in this way. and this is part of what makes the Gabriel synthesis so easy to use.